thank you for coming to my talk. I will be giving you an update on our group's most recent results on zinc oxide nanostructures for sensing applications and for energy harvesters. So I will start with general bulk properties of zinc oxide and give a brief overview of the material and electrical properties. Then I'm going to move on to zinc oxide nanowires and our accomplishments and results on these wires as physical sensors and harvesters. Then I will conclude with a summary and future outlook. So, as you probably most of you know, zinc oxide crystallizes in 3 different structures. At high pressures, it crystallizes in cubic rock salt. If you were to use a cubic seed layer, it will tend to crystallize in cubic zinc blend. But the most importantly, what we are interested in is that at ambient temperatures and pressures, it crystallizes in hexagonal wurtzite, where each zinc and oxide atoms form tetrahedral unit with the oxygen anions and zinc cations occupying alternating planes in here and thus forming a dipole moment. And that gives you your piezoelectricity. So these are the bulk properties of zinc oxide, specifically the piezoelectric coefficients. And what I say is bulk because the nanostructure, as far as the nanostructures are concerned, piezoelectric coefficients and the properties are not only size dependent, they also depend on the stress, which doesn't make them really a constant at all. So there's a lot of unknown in this, and that's why a lot of people use still the bulk properties. One thing to notice is that let's see, 3.1 piezoelectric coefficient here is less than the 3.3 coefficient, which would be, this would be bending, and this would be compression. And when you look at the elastic constant matrix, your 3.1 right here is less than 3.3. So that has profound effect on things. So going on to nanowires. So depending on whether you're going to use the sensor in nanorod, nanowire configuration in bending mode, which means you're doing 3.1, or in compression mode, which you're doing 3.3, you're going to get different results. So we did extensive simulations and simulations on the both bending and compression of these nanowires, and this shows just one of these for bending. And you can see that if I have a lateral force on the tip in for 1 micrometer in y direction, 1 micronewton in y direction, which results in a 54 nanometer displacement here, what I'm getting is about total of 1.3 electron volt difference between the 2 sides. If I do compression and I use the same force, a little bit different length and diameter, such that the top surface is compressed by 0.02 nanometers, what I'm getting is much less because the bottom is grounded, and so I'm getting a voltage difference of negative 0.39 volts. All right. Early development of zinc oxide nanowires, let's give the credit to where the credit is here. And that was done by Dr. Wang at Georgia Tech. And he was the one who started growing these in ordered fashion as an array using a template such that they can really grow in whatever format that he wants. And these are grown in with a hexagonal template so that they grow around in hexagonal. And he used these as nano-sensors and nano-generators. Recently, he moved on to using the zinc oxide nanowires as 3-terminal devices and 2-terminal devices to be able to replace CMOS technology. I think it's far away from maturity right now. But the idea is to replace transistors and diodes. All right, coming to our work. We have built carpets, zinc oxide patches that we call carpets, nanowire carpets, as tactile sensors. These are, as with all other piezoelectric sensors, they are self-generating. You don't need to power them. They are. We built these for the purpose of putting them on conformal surfaces as part of a skin on a prosthetic device or a part of a robotic skin. Therefore, we wanted to make them conformal to non-planar surfaces, so therefore they're bendable, they're switchable, and they're not stretchable yet, but we're working on that. So when you make something bendable, of course, you cannot put them into a regular package. So we built them in between a superstrate and substrate that are both flexible, and therefore they are resistant to moisture and mild chemicals. So we were able to measure the sensor performance with high reliability, high sensitivity, and also negligible. So we built them in different structures, but the general structure is that they are in between a flexible substrate and a flexible superstrate, and that's polyimide, capital not polyimide, and such that the zinc oxide nanorods are grown in an orderly fashion in patches, and there we have access to the electrodes, to the top electrode, and to the bottom electrode. So in this case, it is used as a compressive pressure sensor. So one of the things that you have to worry about in this case, since you have a substrate that and a superstrate that are flexible, when you apply a force on it, you would like the force to be absorbed by the nanowires and not by the squishy flexible substrate. If all of your stress goes into the flexible substrate, you're not going to get much sensitivity. And that, of course, is related to what kind of substrate that you use. So for our specific polyimide substrates, we have looked into how the stress is distributed as a function of thickness of the substrate and the superstrate for from 5 micron to 35 micron for 5 kilopascal and 500 kilopascals. And we were able to see that the thickness of the substrate does not really make much difference. By the way, why 5 kilopascal, 500 kilopascal, 5 kilopascal is a very like a feather-like touch. 500 kilopascal is a fist touch. So tactile rate. All right. So we also looked at the estimation of the generated voltage again for those two extremes, and we've also done in the middle. But this is of a compression of a single nanorod of 160 nanometers with 5 micrometer height, which is something that we can grow. Different sensor designs. We built them in arrays. So a single array or a patch of nanorods, looking at it from the top, and each one is addressable so that we can look at them. We've also put these patches in series. So the bottom of one is connected to the top of the other one. And this is a series of 9, series of 25, series of 100, and series of 49. Yeah, 9, I can't see these, 949. So here is our chip, and you can see that this one says single, and this is 9, 25, and 45. We were able to, please note that we were able to grow these in a very orderly fashion using a template of another polyimide and using NIL. So nano imprint lithography with embossing, so that we were able to grow a single nanowire per hole in the template. And that just took a lot of time. So fabrication process, we actually built these upside down. So we start with a substrate and we grow a silicon nitride isolation layer and the polyimide we spin on. That actually becomes our substrate. I'm sorry, superstrate, not substrate, superstrate. Then we put another silicon nitride layer, and we put a gold seed layer, pattern the gold seed layer, and then we put a gold layer, that's our electrode, and then we put our zinc oxide seed layer with a titanium onyx layer and pattern them. So this is our template, thermoplastic polymer template, which is embossed and lithographied with NIL and embossed. So at this point, if you do a hydrothermal growth, the growth will occur only in the sections that have a seed layer at the bottom and only at the sections that have an opening. And so that's what happens. And then we remove the template and we put another polyimide on and we pattern it such that we have openings to the electrodes. And then this is very important, we back etch. The back etching, the amount of back etching that we do determines the sensitivity. The reason why we back etch is, of course, because we need to put another electrode on top. So that's what we do. We pattern that. Okay, and it looks like something like this when you go into detail. So we deposit more polyimide, and that to make the substrate, etch more, and then we remove the silicon carrier wafer. So what you have now is a touch sensor, tactile sensor, which is made of nanorods, and that is going to go on top right here onto a curved surface that can be attached, and it can be electrically accessed so that this is how it looks like when we pull it out. And microscope images. So we tested these, and the way we tested them is here is a schematic of the nanowires. We've used a nano positioner with a micro-force application and so you could actually apply this with a tip on the patch, either manually or using a signal generator at a specific frequency, and that allowed us to check the frequency. Okay, we looked at crosstalk. Each of these single ones are addressable. So we addressed the first one top left by electrically looking at the probing onto it. Then we put our tungsten tip to at this point going at 25 first force, and we moved it all around to the sensor that is probed, to all of the other sensors around it. So you can see that only when we tap on the one that is probed, you get a signal. So there's really no crosstalk. And this is done manually, and you can see all of the results in here. So from 10 kilopascals to 200 kilopascals. And when you draw the maximum, the response as a function of pressure, you get a fairly linear case, and these are different sensor structures with minimal hysteresis, so going up and going down. And this is a response of sensitivity as a function of number of arrays that you put in series. You can see at a certain point, it doesn't really matter how many of them you put in series, because again, it's only contacts, but you're still limited with the contact. So this is the most recent work that we have, and that is we have doped the zinc oxide nanorods with lithium. The lithium atoms go substitutionally and substitute for zinc oxide, and that increased the sensitivity. So this is our work that is being presented as a poster. It is in the slot called 70 downstairs. Please go and look at it. So we were able to, zero lithium doping all the way up to 25 millimolar a lithium doping. Not only it changed the characteristics, but it also changed the response. And here it is. Please do go see and please look at the paper also. All right. So now I'm going to go into energy harvesters. This is significantly less work, less presentation, it's not less work. So as with a lot of vibrational energy harvesters, this works on the model of mass spring. And this required us to integrate the nano structures with MEMS, which were made of proof mass and spring. And when they are compressed or when they are vibrated, that causes the nanorods to generate energy. And so here is our general structure. We have our nickel proof mass, and we made it in like a waffle to decrease the stress. And under this, right here, is the zinc oxide nanorods vertically aligned. And we have access electrically to the bottom electrode and the top electrode, which is the zinc oxide proof mass, through the substrate and the superstrate. So when they're built, and again, the amount of back etching that you do, the same as what we've done with the tactile sensors, determines not only the modulus for flexibility, it also determines the sensitivity that you're going to get. And you can really play with that to change the modulus of elasticity and also change the response. This is the proof mass, nickel proof mass, and under it there are the embedded the nanowires. So this is a combination of a Liga process, let's say UV Liga, and so-called Prudence Liga, and also a nanostructure hydrothermal growth. All of them are so results for the generated power, and you can see that the power generated decreases as a function of shaker vibration. So these are vibrational energy generators. This is actually good news because the problem of energy generation for vibrational energy generators is the lack of good energy generators at low frequencies. All right, So summary in outlook. All right, zinc oxide. I don't need to sell you zinc oxide probably. So zinc oxide nanowires are very, very versatile. However, there needs to be a lot more material property investigations because everyone still uses bulk material properties. I'm not a material scientist, so please, we need nanostructure properties. The biggest is yet to come. We need to look into doping with lithium and other substitutional impurities. We need to look at other structures. Nanorods are pretty much done. Nanobelts. Integration to MEMS is a big challenge because you're looking from nano to MEMS configuration. And then, nobody has, as far as I know, done any post-CMOS processing. So how do we integrate? And bibliography, again, a little bit plug for the poster. And thank you.